All right, so we're going to continue on here. We were in chapter 2 last week, and in chapter 2, we were talking barely about units. And remember, as we talked about, there's kind of two types of units. There's kind of the US units, or the English units, and the metric units. And again, sort of a combo of those, which really is more the metric, is the SI units. And again, that's the sort of that standard system of units that we talked about, that they sort of came up with because, again, everybody's sort of using different units can create some issues. So remember that we then talked about sort of two types of numbers. One that is a measured number, and a measured number is usually associated, obviously, with a measurement. So we have a number that's a measured number, and we have an exact number. And a measured number, as I mentioned, is coming from a measurement, and will have a specific number of significant figures associated with it based on the measurement that you take. Well, an exact number is really two things, or one of two things. It can be something that is counted, or something that is considered a definition or an exact definition, like 1 foot is 12 inches. Where this really comes into play is, as we'll talk about today, when we're doing calculations and sort of how many significant figures your answer should end up with. If it is an exact number, it's considered to basically have as many significant figures as you want, an unlimited number of significant figures. And as we'll talk about, basically what that means is the good thing in a calculation is if you have an exact number, you really don't have to worry about it in terms of your answer and how many significant figures your answer should have. You really just have to focus on the measured numbers, and that's the one where we're going to really sort of figure out how many sig figs our answer should have. Now, we talked about taking proper measurements, and again, a reminder that whenever you take any type of measurement, there is always going to be some degree of uncertainty associated with that measurement, really some degree of estimation that has to occur. So as we looked at, say, this ruler, and we want to always, when we are taking any type of measurement, we really want to figure out kind of the two different markings, if there are two different markings, on a particular piece of equipment. As we talked about last time, sometimes the first type of marking is referred to as the large marking, and those are usually the ones that actually do have sort of numbers kind of next to them. And as we talked about last time, in this case, we have a marking at 1 centimeter and we have a marking at 2 centimeters. So if we want to kind of figure out the difference between the two markings, or how much that represents, we could just subtract the two of those numbers. And again, that means that each of the large markings in this case represents 1 centimeter. So as we go from here to here, that represents 1 centimeter. The other markings that we have on there are sometimes referred to as small markings. And small markings are typically ones that actually do not have numbers next to them. And they're all the markings that sort of lie between the two large markings. So once again, we want to make sure that we do count these properly. So when we are counting the small markings, remember that we do start counting after the last large marking, which means in this case, we would start counting here. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. And we would end at the next large marking, which would be 10 there. And what that tells us is there are 10 small markings between each of the larger markings. So if you're not sure, all you have to do is just divide the large marking by how many small markings there are. And that will tell you that each of those small markings represents 0.1 of a centimeter. Again, this would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and a 2. And that is always the kind of the two things you want to really sort of figure out when you're taking a reading. And it does change depending on the piece of equipment that you're using. So you always want to kind of look at the scale and figure what those two things represent, the large markings and small marking. Now, when we do take a reading or a measurement, there should always be some numbers that really, no matter who looks at it, everybody should agree. So once again, no matter who takes a look at this ruler, everybody should at least agree that my arrow there is at least 1.3. And it is customary to record what are sometimes referred to as all the certain numbers. And again, these are numbers that there really should be no disagreement about. Anybody that takes a look at it should agree it's at least 1.3. Now, where perhaps maybe some disagreement may come into play, some estimation or uncertainty is, again, when we look at that arrow, it is definitely not at the 1.3 mark. It's not really at the 1.4 mark. It is somewhere between. So I may look at it and try to visualize, all right, I think like half-ish is there between those two markings. So maybe it's sitting on half, and I record a 5, and obviously the units. That number I just recorded is what is sometimes referred to as the first uncertain number. Now, again, somebody else may look at it and go, I don't really think it's halfway there. I think maybe it's a little less than half. And it's okay. You can record like a 4 if you wanted. Or maybe you look at it and go, I think it's a little further than half in some situations. You can record a 7. If it looks like it's almost to the 1.4 line, but not really right there, you could record something like an 8 at that last one or a 9. So you do want to kind of break up the distance between those two markings and try to figure out about where it is. So clearly, if my arrow extended to like here, we wouldn't probably want to record 5 at the end. We'd probably want to record something closer to maybe an 8 or a 9 at the end there. Again, because obviously it would be much closer to the 1.4. Now, the importance of doing this, as we talked about last time, is when you record all the certain numbers and that first uncertain number in a measurement, that is what is known as significant figures. And again, that means in this particular case, this number would have 3 significant figures. The estimated digit here obviously would be the 5. And what we're really saying when we do this is, I think it's 1.35. But, maybe it's like 1.36, maybe it's a little less, maybe it's 1.34. But the uncertainty here lies within the second decimal place, or the hundredth place there, in that particular measurement. Any questions on that there? Now, as we talked about last time as well, you can typically take your reading to one more place to the right of the smallest marking. So you typically could go one more place to the right of the smallest marking when you take your actual reading. Here we went to 2 decimal places. The smallest marking represents 1 decimal place. Not in all cases. I think we did one at the very end there where it went by 2s, right? So you couldn't go obviously one more place to the right. So, but in 9 times out of 10, you could typically go one more place to the right. As we also talked about towards the end last time, if you are extremely confident about what the smallest markings represent, so if you look at this and go, I'm for sure, I know it's 0.1 represents the smallest markings, but you're maybe unsure of how far you should take your reading to, you could always just take the smallest marking. And again, if you're confident on what that represents, divide it by 2, and that basically will tell you how far you should take the reading to. So if we did that in this case, if we took the smallest marking, which represents 1 centimeter, divided by 2, you end up with 0.05. That is 2 decimal places. And once again, that is how many decimal places we should take the reading to. So again, if you're kind of confident on, I know what the small marking represents, but maybe a little unconfident how far you should take the reading to, you could always just take the smallest marking divided by 2. It will probably always come out to like something with a 5. That doesn't really matter. If it goes to 1 decimal place, that's how far you should take the reading to. It goes to 2, 3 decimal places, that's how far. That even works with that scale we saw last time where I think we had something like this. Maybe a graduated cylinder or something. And again, in this case, our large marking is a 10 and a 20, which the difference there is 10 milliliters. Again, if you just subtract 20 from 10, you end up with 10, and that is the volume difference between those two markings. When we look at how many smaller markings there are, again, there was 1, 2, 3, 4, and 5. And if I take the big marking divided by how many small markings there is, that tells me in this case each of the small markings is actually 2 milliliters like we saw last time. That means that this guy is 12, 14, 16, and 18. So much like that example we had last time, if we find ourselves kind of between here with our meniscus, which looks very straight there, between 14 and 16, as we talked about last time, is actually 15 is the number between that. And in this particular case, that is the best you can do, because when we look at the difference between these two markings, that is basically 2 units, which means, as we talked about last time, you really don't know where 14 ends, where 15 starts. You can't really just break it up that way. That's too many numbers in that small distance. So once again, if you got to something like this and you're like, well, I'm for sure each little guy represents 2. All you have to do in this case, again, is take 2 divided by 2, which is 1 milliliter. 1 milliliter is a whole number, and that is what you took your reading to. No decimal points or anything like that. You took it to a whole number, and that's the proper reading here. That, again, like we talked about last time, would have how many significant figures? No, I just held it up once to see if somebody said it. 2, yeah, so it has 2 significant figures in this case. And these guys here would be 2 significant figures. The uncertain number in this case would actually be the 5, right? The estimated digit in this case would be the 5 in this particular case. Any questions on that there? All right, so let's just take a look at one more sort of example here to talk about something that people often sort of incorrectly do, maybe. Let's go back to that sort of ruler example. So we got the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say we were measuring our arrow, and let's just say it was like dead on that particular marking right there. Now, obviously, this is the same scale we just used previously, so we know the large markings here represents 1 centimeter. The small markings represents 0.1 centimeters. And obviously, that would mean in this case, when we look at it, 1.1, 1.2, 1.3, 1.4, obviously, and so forth. So when we look at this and we want to record our measurement here, it is definitely on the 1.3. So I record 1.3 centimeters, 1.30 centimeters, 1.30000, why not 000 centimeters? Not quite sure how you get there, but I'll go with that. Is there a difference in how we record it? Does it matter in this particular scale? What do you think? I'm going to say it probably does, or I probably wouldn't ask this question, I imagine. But let's see why. Let's just take the first one over here. If we recorded this value here, because I'm like, it's dead on the mark, I'm going to record 1.3, sounds good to me. How many significant figures does this number have? It does have 2 significant figures. What is the uncertain number in this one? It is the 3, or the estimated digit, right? So when we record it as 1.3 in this case, we are recording only 2 significant figures on this particular scale. And what we are saying is, for example, I think it's 1.3 centimeters, but hey, maybe it's 1.4, and maybe it's a little less. It's somewhere in there, right? Because the uncertainty here is lying in this digit, right? That's where we're sort of guessing. So when we look at the actual scale and the picture here, we are basically saying, I think my measurement is somewhere within that little sort of horseshoe there. Is that a lot of error or a little bit of error? That is a lot of error, right? My real measurement is sitting in the middle of it, right? And that's a lot of, I'm not really sure, right? So when we look at this measurement, this guy would have how many significant figures? Would have 3 significant figures. The uncertain value in this one would be? It would be 0, yeah? So when we look at this particular measurement, we're saying I think it's 1.30, but the uncertainty is actually over here, which means maybe it's 1.31, maybe it's like 1.29. That is like this much error. That is more reasonable on this scale, right? Because we could clearly see our marking is within that blue, basically, right? Which one's the better measurement here? The second one. Which one's the correct measurement here? It is the second one. Because on this particular scale, we are able to go to the second decimal place. You do need to include a 0 here to maintain the proper number of significant figures. You may be saying, but isn't 1.3 and 1.3 the same number? It is, but it does not have the same significant figures. And by killing or dropping off the 0 here, you made your measurement pretty crappy, a lot crappier than it should be based on the scale that you're using. You basically just made your thing worse than it should be. You could do a lot better based on the scale that you have. So you never want to lose significant figures when you're doing that. And it happens a lot, especially when things hit like right on a line. People just go, cool, I know what that line represents. I'm just going to write the number. But you still need to think about the significant figures. You still need to realize how far you could take the reading to. And once again, if you just divided this like we talked about by 2, the smallest markings, you would end up with 0.05. That is 2 decimal places. And that is the proper reading here. So sometimes when you do take a measurement, if it happens to be right on a line or something like that, you do need to still think about your scale. And if you can, based on that scale, for example, here, go to 2 decimal places, you need to add a 0 to maintain the proper sig figs. Otherwise, you just made your measurement a lot worse than it should be with that scale. First off, any questions on that? Now, on the other end of the extreme, how many significant figures are in this guy? I'll trust you. I was just writing zeros. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 10 significant figures. The uncertain number would then be way over here, right? Is there any way on this particular scale that I could take a reading to that many decimal places? There is no way, right? So just like you shouldn't lose some zeros, you shouldn't add extra zeros, because what this says is over here, that's a way better measurement than you could ever dream of taking on this particular scale. So you don't want too many zeros because it makes your measurement better than it should be. You don't want too less zeros or significant figures because it makes your measurement worse than it should be. You want the exact correct number of significant figures based on the scale that you're using. That way you have the proper number of significant figures and you took a proper reading. Any questions on that? Yeah. It does matter. We're going to talk about it shortly. We're going to officially talk about kind of how to count significant figures. These zeros do count because there actually is a decimal point in the number. So technically speaking, all those zeros, they would all be significant in this case, yeah. And it, in theory, would have came from measurement, which would make them significant in that case because of that decimal point. Other questions? Okay. So again, if you hit the on the nose, you got to think about the scaling and how far you can take that reading to. So that's usually something you want to kind of work out before you take the reading. Just take a moment, look at the scale, and go, okay, on this particular scale, I could go to the whole number. Or this particular scale, I could go to 1 decimal place or 2 decimal places. And then all your numbers should obviously be appropriate based on that. All right. So here again, just taking a look at some examples. If we take a look at this particular scale here, in this case, our large markings represents 1 centimeter. What are the small markings in this case represent? Are there any small markings between the large ones? There are not, which means in this case, the large markings and the small markings are the same. They're the only markings on it. And in this case, the small markings would actually be 1 centimeter as well. They would be the same in this case. That means when we look at this, it is definitely 4. Now, again, like I was talking about before, this is the smallest marking. If I divided it by 2, that gives me 0.5 centimeters. That is how many decimal places? That is exactly how far I should take the reading in this case. So that tells you exactly how far you should take it to. So if I just wrote 4, it is wrong, right? It does not have the proper number of digits based on this scale. Here we're going to estimate how far, whatever that is, between the 4 and the 5. Again, maybe you feel like it's in the center. You would record 4.5 in centimeters. The uncertain number here going to be the 5. And the certain number should be the 4. I'm sorry, yeah, the 4. In this case, we could only go to 1 decimal place because of the markings in this particular case. Any questions? All right. And that's what they agree, so that's good. Here we got a few extra markings like we've been talking about. Once again, if we just look at the difference between 3 and 4, that's going to give us 1 centimeter for our large markings. If you count up all these little guys, there's going to be 10 markings. So again, you could divide this by 10, giving us our 0.1 centimeter for the small markings. And again, you could take the small markings divided by 2, 0.05 centimeters. That tells me when I'm done with my reading, how many decimal places? I should have 2 decimal places when I'm done, right? So we come here and go definitely 4. This is 4.1, 4.2, 4.3, 4.4, 4.5. So 4.5 is a little bit more than that. It again, they estimated halfway through there, giving us our 4.55. The very last 5 here going to be our estimated digit, our uncertain digit. This number again would have how many significant figures? It would have 3 significant figures. All of them would be significant in this case. So all the certain numbers plus the first uncertain number would be the number of significant figures there are. And just like we talked about a second ago, if our little wood block there ends up right at the 3 on this particular scale, again, we roll through our normal procedure, large markings, 1 centimeter difference. Anyone you want to subtract to 2. Small markings also going to be 1 centimeter difference because, again, there is no real small markings, so the large markings are the small markings here. So since I know my small is going to be 1 centimeter, divide by 2, 0.5 tells me I need a decimal point here. Now I'm exactly at 3, so once again, we record 3, and because of the scale, I know I need to go out 1 more. I will add a 0, giving me 2 significant figures here, with the 0 being the uncertain number. Any questions on that there? Mm-hmm. Okay. All right, why don't you give this a try as my scale went somewhere. I'm not really sure. Let's measure the red marking. This is the 8 marking. This is the 9 marking. That's the 10 marking. These obviously are centimeters. What should be the proper reading there? My picture got moved around a little bit. Okay, so let's take a look. Once again, should always sort of be your process when you're taking a measurement. You just want to figure out those two things. Because if you don't figure out those two things, what the large markings represent and what the small markings represent, you're going to be in trouble, obviously, with your measurement. So let's start with the large markings. In this case, our large markings represents how much? 1 centimeter, right? So it could take 10 minus 9, gives me 1 centimeter. Now I want to count up how many of the small markings there are between those large markings. I'm actually going to go over here and count it so I don't mess up kind of over here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are on this particular scale 10 small markings. If you're not sure, just take 1 divided by 10. And that again will tell you that my small markings is going to be 0.1 centimeters. Now that I know for sure that my small marking is 0.1 centimeters, if you're still not sure how far you should take the reading to, I'm going to divide that by 2, and that tells me 0.05 centimeters. That means when I'm all said and done with my measurement, how many decimal places should I have? Should have 2. So let's go see what it is. Obviously, I'm imagining it's that one, but let's make sure. So here, it is definitely 9.1, 9.2 in that case. And it looks like maybe it's right on the 9.2 mark. So we go with 9.2. And again, if I wasn't sure and I just recorded 9.2, how many significant figures does this have? 2. The uncertain mark then in this case would be the 2. And we know already by doing this that that is not correct, right? Because I need to take it to 3 decimal places. So again, it's right on the marking. This would be a case where I do want to add a 0 in this case. Because this scale tells me every reading should go to 2 decimal places. That would mean in reality, this measurement has actually how many significant figures? 3. And which one's the uncertain number, the estimated digit? Yeah, the 0 here is our uncertain. And that is what we see when we look at this scale. We're basically saying, I think it's 9.20, but maybe it's like 9.19, maybe it's 9.21. That is an uncertainty right about there, which is actually where the line is, right? As opposed to if you just did, like we talked about earlier, 9.2, you're saying, I think it's 9.2, maybe it's 9.3, or maybe it's 9.1, where the uncertainty would be here. That again is telling me, I think my measurement is somewhere in that area, which is a lot more error that you should not have based on the scale. And again, you would have made your measurement worse than it should be based on the scale that you have. So again, we do want to have our proper number of digits. Yeah. Any questions? Yeah. Yeah. If you put 9.22, you would be fine. Again, that's basically what that last digit is in this particular case. It's the uncertain digit. So if you looked at it and felt like it really wasn't exactly on the marking, maybe you felt it was a little bit over. If you laid up the proper number of significant figures based on that scaling, I think it would be okay. Now again, if you wrote like 9.29, clearly is nowhere near the next mark, right? So maybe you would lose that. But if you're just like near that mark and you have the proper number of digits, you should be okay. Yeah. Other questions? Okay. Oops, maybe. Oop. Let's try one more here. No, that's the same one. Let's not try that one. All right. All right. Any questions on how to take a proper measurement there? All right. Now that we've kind of talked about what significant figures are and where they come from, they do come from obviously our measurements and our measured values. Let's talk about how we count significant figures. What counts as a significant figure? What doesn't count as a significant figure? Who knows? We'll see. Maybe we know. We'll see. So let's start with the idea of the easy rule on significant figures, which is if you have any number that is not a 0, you're good to go. Those are always going to be significant. So as it says there, any non-zero is going to be a significant figure. So if we had 3265. When we have a number here and we're assuming maybe it's a measurement, we always start counting left to right on the number, and you do not start counting your significant figures until you hit the very first non-zero. So that's an important thing to remember as soon as we get into zeros, counting zeros. You don't actually start counting your significant figures until you go left to right and hit the very first non-zero number. In this particular case, it happens to be the very first number is a non-zero, so that is where we actually start counting. That's a non-zero, that's a non-zero, non-zero, and non-zero, which means that this number should have 4 significant figures. They are all significant. That would also mean that obviously if this was a measurement, it has 4 significant figures. The uncertain number in this case would be which one? It is 5 in this case. Now, I'll say this now and we'll see it in just a second, but the uncertain number, or the estimated digit, is not always the last one written. So people think it's always the last number that you see written. It is not always the last number written. It should always be the last significant figure that is written. So the last significant figure going left to right is always where the uncertainty lies. I will say 9 times out of 10, probably going to be your last number, but there are times where it is not the last number, and that is not where the estimated or uncertain digit lies. All right, so let's get into zeros. And zeros is really the thing that gives people sometimes a hard time. So there are 3 types of zeros. The first one are referred to as leading zeros. Those are not significant. So leading zeros are not significant. So if I had a number written like so, 0.000323. Once again here, I'm going to start counting my significant figures left to right. I'm going to start counting my significant figures when I hit what type of number? A non-zero. So I'm not counting until I hit a non-zero, which means as I go left to right, I have not hit a non-zero until I get to right there. As soon as I hit that first non-zero, now I'm counting significant figures. So that's significant. That's a non-zero, which means this guy's got 3 significant figures. All those zeros that come before are not significant because we have not really started counting yet. We haven't hit our first non-zero number, and we do not start counting until we hit that one. Any questions on that there? Next one is sometimes called a trap zero or a captive zero. Those are going to be significant. And these are zeros that are trapped between 2 non-zero numbers. So if I have a 404, once again, we're going to start counting on the left. This is our first non-zero number, which means that is where we start counting our significant figures. This 0 is trapped between 2 non-zero numbers, which means it's significant. And that is a non-zero number. This guy right here, 3 significant figures. Uncertain number in this one. Which one was the uncertain number in this one? It is the 3 is the uncertain number, right? How about here? Which one's the uncertain number in this one? It is the last 4 in this case, right? Any questions on those there? Then let's talk about the zeros that screw everybody up, which is the trailing zeros. These are zeros that come at the end. So trailing zeros, they may or may not be significant. They are going to be significant if there is a decimal place or decimal point written in the number. So this is a little bit different than what we were talking about with scientific notation, where if we have a number, we just kind of assume there's a decimal point at the end. Here, it actually does need to be written. So if you don't see a decimal point in the number, the zeros that come at the end are not going to be significant. If you see a decimal point written anywhere in the number, all the zeros at the end will be significant. So if I had this, 600, how many significant figures would this one have? It would only have one. Again, we're going to start counting left to right. That is a significant figure. These are zeros that come at the end. There is absolutely no decimal point actually written in that number. One significant figure, yeah. Now, if I take my 600 and lay myself up a decimal point at the end, how many significant figures does it have? And now has 3 significant figures. We're going to start counting. Zeros at the end are significant because there is a decimal point written here. This would have 3 significant figures. The uncertain number in this one here on the right is what number? Where is the uncertainty there in that one? It is the very last zero, yeah? Is the uncertain digit in that one. How about this one? Where's the uncertain digit? It is the 6, not the end of the number. So this is what I was talking about before. The 6 is the last significant figure there. It is not the end of the number. So once again, when you're looking at which one is the estimated digit or uncertain digit, it is always the last significant figure that's written, which may not always be the last number written in this case. Yeah. And that is because when we have if this was a measurement, 600, we're saying, well, let's call it like meters or something. We're saying, I think it's 600. The uncertainty is here, so it could be 700, or it could be like 500 meters. That is a lot of uncertainty between those numbers, right? That's a pretty big one. Not the greatest measurement taken, right? This one, when we write it like this, 600, and we'll just say these are meters. We're saying, I think it's 600, but maybe it's like 601, maybe it's 599. Uncertainty back in this digit, a much better measurement, right? A much more accurate probably measurement, or better measurement in terms of significant figures. So again, this goes back to what we were talking about earlier. You don't want to lose significant figures when you're taking measurements because, again, it makes things worse. And it is compounded because, as we'll talk about, when you do a calculation, your calculation is only as good as like your worst measurement, yeah? So if you decided, I want to record my measurement like this, when you're all done and you're going to use this in a calculation, you would probably end up with one significant figure, which means not the greatest calculation probably. That's a lot of error within that measurement. Here, you would have a lot more significant figures probably in your answer when it's all said and done. Any questions on that? We also talked about earlier in the previous chapter that if you have a number that's written in scientific notation, all the numbers before the times 10 part are always significant, right? So if I had 1.25 times 10 to the 2, how many significant figures would that have? Yeah, all these would be significant. So if the number is written in scientific notation, any number that is written before the times 10 part, like we talked about in that previous chapter, is always going to be significant. And again, as I also mentioned, sometimes the only way to give your answer the proper number of significant figures is to write it in scientific notation. Because again, as we talked about in that chapter, you can kind of control your number of sig figs. If I only needed 2, I could write 1.3 times 10 to the 2. You know, if I needed 4, I could add 1.250, and I could add or take away numbers and put it in the right significant figures. Remember as well that if a number is written in scientific notation, that is where you should look in terms of significant figures. People always want to convert it again into like a decimal form and then try to figure out significant figures, and you probably will get it wrong. So it's written in scientific notation for a reason. It has a specific number of significant figures written in scientific notation. So you want to look at it written in scientific notation to determine how many significant figures it has. Any questions on any of that? So if I had a number like 0.000040032001000 centimeters. I'm not sure how you do that. How many significant figures would this have? I have no idea. We were counting wrong. All right, let's see. Let's take a looky. All right, let's go through it. We're going to go left to right. Are any of these significant? They are not. The reason they are not significant is because I haven't hit the first non-zero number yet, right? My first non-zero going left to right is 4. Now I should start counting, right? I then run into a couple of zeros that are trapped between non-zeros, and those are going to be significant. And that means that's significant, non-zero significant, non-zero significant. Trapped zeros again, going to be significant. Significant. Now it brings us to the zeros at the end. Are they significant? How many people say yes? How many people say no? How many people aren't sure? It's an honest answer. All right, so in order for the zeros at the end to be significant, what does the number have to have in it? Does this number have a decimal point in it? It does, way back here, right? That's a decimal point? Yeah. And even though the decimal point's way back here, it is still written in the number. And that turns all of these guys into being significant. So let's see how you did there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 significant figures. The uncertain digit in this case would be the very last zero. Yes. And I think that has all the zeros in it, that particular one there. Now, sometimes people get into this question or ask this question, which is, wait a sec, you just told me this is a decimal point. And I can see when I look at it that these zeros come after the decimal point, right? And they are not significant even though they come after the decimal point because we had not hit the first non-zero. So we had not started counting our significant figures. And even though they are after the decimal point, those zeros, they are still before the first significant figure. And that puts them as not trailing zeros, but those are leading zeros, leading into the first significant figure. Any questions on that? So sometimes people think, well, they're after the decimal, so they should be significant. But again, we do not start counting in this example until we hit that 4. Yeah. Any questions? I hear somebody asking. I'm sorry. Yeah. Is that you're talking about the 4? Yeah. Yeah. So you always just want to go left to right on the number. And again, just think to yourself, I'm not going to start counting sig figs until I hit the very first non-zero. Once I hit that first non-zero, now you should be counting. And now you got to decide, okay, any zeros that came before that first non-zero are going to be leading zeros. You don't have to worry about. Now, once you hit the first non-zero, any zeros you come across will be one of two types. They will either be a trap zero, which will be significant because it's between two non, or there will be zeros at the end, which will be either, again, significant or not significant, depending if there's a decimal point. Other questions? Okay. All right, so we take a look at some of these rules we were talking about here. Here, anything that is not a zero going to be significant. So these both are going to be significant, with the 5 being the uncertain. All of those numbers are going to be significant. Here we would start counting at the 2. The 0 would be significant because it's trapped, and the 5 would be significant as well. And again, we have our guides in scientific notation. So that has 2 significant figures, the first one, 3 on the second, and our zeros at the end here, no decimal written. So it's only one significant figure, which would be the 5 in this case. And here, zeros at the end, but there is a decimal point, which makes them significant. Now, why do we need the 0 at the end if there is no decimal? It's important because in this particular case, you would write 50, which has one significant figure. But if you just wrote 5 liters, which is one significant figure, is there a difference between those two numbers? There's a big difference between 50 and 5. So again, here we don't want to drop to 0 thinking it's only one significant figure, because we now definitely change the meaning of those two values, right? Because there's a big difference. So that's also, as we'll talk about shortly, something to keep in mind. In an effort to get the right number of significant figures, you definitely don't want to do some crazy rounding, yeah, and change ever the meaning of the number by doing so. All right, so again, all guys are non-zero. Going left to right, we got 4 in the first one, 2, 3, and 5. And again, on each of these, we're counting here and going to the right. Here, we're going to start counting here, trap zeros, everybody's significant there. Here, we're going to start counting there, trap zero, significant. Once again, we are not counting until we hit the 7 in this particular case. And now we have a trap 0, which is significant, and obviously the 2 at the end. Once again, we are not counting here significant figures until we hit that first non-zero, which is the 4. And we got 2 trap zeros and 2 5s, and that gives us a total of 5 significant figures in this particular case. Any questions on those there? Again, we're going to start counting here. No decimal written. These are numbers at the end. They are not going to be significant. Here, we're going to start counting. All these zeros at the end are going to be significant because there is a decimal point written in that particular case. In the case of the 200 minutes, the uncertain number is which one? The 2. In the case of the 40.00, the uncertain number is the last 0, right? So again, not always the last digit written is the uncertain number. A lot of times it is, but again, this is the case where you got to be careful. She used to like to put in the lab manual, this one is one of the problems, and that would have how many significant figures this number? And the uncertain number would be? It would be the 2, right? As those are the only significant figures there are. And again, the definition of significant figures is all the certain numbers plus the first uncertain number, which is your estimate. So since this only has 2 significant figures, that 2 has to be where the estimate is. And again, it's not a great measurement if this was a measurement, because you're basically saying, I think it's 12,000, could be 13,000, could be 11,000. That's a lot of could be's, right? That's a lot of error within that measurement. All right, we got the idea on those. Now, when you do write a number in scientific notation, or you take a number sort of out of scientific notation back, you do want to maintain the proper number of significant figures, especially when you're kind of going from regular sort of form there to scientific notation. So when we look at this 500, the way it's written, it has 3 significant figures. Again, starting to count here, these zeros at the end are significant because of the decimal point. So if we wanted to write this in scientific notation, we would assume that we're going to go 1 place to the left, 2 places to the left. That gives us 5.00 times 10 to the 2 grams. Why should I not write it like 5 times 10 to the 2 grams? How many significant figures would it have in that case? 1, right? When it had originally 3, which means by doing so, I just made my number a lot worse than it should be, right? So in this case, we do need to keep those zeros to maintain the proper number of significant figures when we turn it into scientific notation, as all of those numbers before the times 10 part are going to be significant. Now, when we come to this guy, the second one, 400,000, we're going to assume here 1, 2, 3, 4, 5 places. Remember, we're going for a number between 1 and 10. Cannot be 10, can be 1. And that's going to give me 4 times 10 to the 5. The original number here has only 1 significant figure, right? There is no decimal point written here, even though we assume it's there for scientific notation purposes, but it's actually not written there. All those zeros are not significant. That means when I turn it into scientific notation, I actually need to get rid of the zeros here, right? And now I have still one significant figure. If I wrote it like this, how many significant figures does it have? That's a lot. 3, 4, 5, 6, right? And now it has way too many significant figures based on what our real measurement is. The reason that's important is we're now saying our uncertainty is back here, when in reality our uncertainty is actually over here. So just like before, and also with scientific notation, you don't want to put extra zeros in there to make it look more sciencey or chemistry like. You want to make sure you have the right numbers. So as you go from positional notation or just like a regular number with a decimal into scientific notations, you should maintain the same number of significant figures. And again, that may require you to get rid of some zeros maybe, or some other numbers as well. And it may require you to add some zeros to sort of maintain it as well. Any questions on that there? As I mentioned earlier, there is sometimes only one way to kind of get something there. So let's just say I had, let's say I had 12,000 written here, right? Centimeters. And I wanted to give my answer. Maybe I did a calculation and I know my answer should be 3 significant figures. Is there any way I could write 12,000 and get it to 3 significant figures in like decimal form? In this case, how many does it have to start with? The 12,000 has 2 significant figures, right? So it has these 2 right here, which is 2 significant figures. That's close to what I want, but that is not really what I want. Can I do a $1.20 with a decimal? Is that 3 significant figures? It is 3 significant figures. Is that okay? That's good. You shook your head. I'll use my example of, let's say I owe you $12,000. For whatever reason, I owe you $12,000. Only like the third day we've seen each other. But I owe you $12,000. And I say, hey, I'm going to give you 3 significant figures. Here's 120 bucks. Am I going to be good with you? Probably not. You look friendly, but you might be a little upset with that, right? There is again a very, very big difference between the number 12,000 and 120. It does not mean the same thing. Although you managed to get yourself to 3 significant figures, you also managed to change the meaning of that number significantly, and that's no good. So you don't want to do any extreme rounding when you're trying to do that. There is no way to do it. Again, if I laid myself up a decimal point right there, how many significant figures do I have? I have 5 actually, and still the same problem because that number now is still 120, right? Not 12,000, so not good. I throw myself a decimal at the end going, why not? That now has how many significant figures? It does have 5. Still 12,000, which is good. You'll probably be happy with that. At least still 12,000, but does not have the right number of significant figures we need. There is no way that you could turn 12,000 in a decimal form into 3 significant figures. The only way you could do that is a little scientific notation action, going 1, 2, 3, 4 times 10 to the 4. Now I have 3 significant figures, and I still have the same meaning it should be, which is 12,000. So when you do calculations, sometimes it does occur that way, that the only way that you can actually get the number to the correct number of significant figures is you have to write in scientific notation. So there are going to be some times where that will happen when you do a calculation and go, there's just no way to get it any other way. Any questions on that there? Okay, we're going to continue on. Any questions so far on what we've been talking about? No? All right. So why don't you take a moment here, and for each of these, write this number in proper scientific notation with the proper number of significant figures, and see what you come up with for each of these. Yeah. look. So obviously here we want to write these numbers into scientific notation. Since we just talked about whenever you're taking sort of a number like this into scientific notation, you do want to make sure you maintain the proper number of significant figures. So starting with A, how many significant figures are there? That is two answers. Let's see how we did. All right, so starting left to right. Am I counting yet? Where should I start counting? Right there at the two. So that is significant. That is significant. That is significant. Is the zero at the end significant? It is because, again, there is a decimal point. Does not need to be next to the zero, just needs to be written anywhere in a number. So we do have four significant figures. Remember, we want to turn this into a number between 1 and 10. That means we do need to take our decimal point over to the right 1, 2, and 3 places. And we do need to keep all of those guys. 10 to the minus 3, small number, negative exponent, right? This number now has four significant figures to match the four significant figures in our original number. Any questions on that one there? Going next one has how many significant figures? Yeah, all of them are significant, right? Gonna start counting here. Everybody's significant. We just need to go one place to the left in this case, giving us 4.3026 times 10 to the 1. Big number, right? Positive exponent. Again, all these significant, matching number of significant figures, 5 in each of them. Yes. Any questions on that one? I don't know who went first, but go ahead. So remember when we do scientific notation, it has this sort of form that we talked about in the first chapter. That has to be a number between 1 and 10. It can't be 10. It's got to be less than, but it has to be a number between 1 and 10. And obviously we had 43.026. If we went in the other direction, we would actually make it now 430, which is definitely not going to a number between 1 and 10. So we do need to go this way, which takes us to 4.3 and some change, which is a number between 1 and 10. Okay, yeah. 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 You need to go however many places that will get you for this first part a number between 1 and 10. And again, it can be one's okay, but it can't be 10. So it's got to be 9 point something or 1 and above. Yeah. So. Yeah. No, it has to be the actual like a number between 1 and 10. Like I told you to pick a number between 1 and 10, it's got to be one of those numbers, yeah, with some decimal places and stuff like that. So, and obviously, like we just talked about, if you went to the right there, that's going to now make it like 430. If you went even more to the right, it's now 4,000. Definitely not a number between 1 and 10. Yeah. Other questions? All right. How many sig figs on this one? It is 4. We're going to stop right about there, yeah. Uncertain digit, by the way, is that last 4, yeah. There is no decimal point written here, but for scientific notation, we are going to assume it is here, even though it's not written, which means we need to go this way. 1, 2, 3, 4, 5, and 6 places. We should keep 1.044 times 10 to the 6. That is a positive number because it's a large number, and we move the decimal place to the left. Same idea with this one. Again, if we just went, if we went to the right, we would add a 0. Now it's getting bigger, right? And definitely not getting closer to a number between 1 and 10. So we need to go in the other direction. And we have to keep going. We have to keep going because if I stop there, I'm at 104,000, which is not a number between 1 and 10. I'm at 10,000, still not. So I got to keep going until I get that important part, as it zooms up, that number between 1 and 10. Yeah. Yeah. We only I scribbled a lot on there, but I believe the decimal point was after the 3. And yeah, so to get us our number between 1 and 10, we just had to go one more place there to the left. Yeah. And that's basically that's how far you move that decimal until you get it to a number between 1 and 10. And again, it can't be 10, it got to be less than that. Other questions? All right. All right. So we talked a little bit about this earlier, but let's talk a little bit about it again here. Exact numbers. Exact numbers are numbers, again, obtained in one of two ways, either by counting or a definition, like 1 foot is 12 inches or 1 kilogram is 1,000 grams. As I mentioned earlier, if I had two baseballs just sitting there, we're not going to do any type of weird measurement to figure out how many baseballs we got sitting there. We're just going to simply count them, and that's considered an exact number. Anything that is a definition like this or like this is considered an exact number. As I mentioned before, when we do have something that's considered an exact number, it really could have sort of unlimited number of significant figures. And again, what that means is we'll talk about here shortly. It's actually a good thing. We don't have to worry about them in terms of our calculations. So we only have to worry about those guys that have a certain number of significant figures, those measured values is really what we have to kind of worry about. Now, what are considered exact numbers? For sure, if you have any type of metric to metric conversion, like 1 meter is 100 centimeters, 1 kilogram is 100 grams, definitely considered an exact number. If you have any US or English to English conversion, like 1 foot is 12 inches, it is considered an exact number. You don't have to worry about it in your calculation. The only time that you have to worry about significant figures when you have a conversion, for example, that goes between the two. So if you have a metric to US or English or an English to metric conversion, you do have to actually look at the significant figures when you're doing a calculation. So that's the only time you got to kind of worry about it. There are a couple that are considered still an exact conversion, even though they're English to metric. The most common one is 1 inch is exactly 2.54 centimeters, even though that is an English to metric conversion is considered an exact conversion. But other than that, if you're going like milliliters to quarts, you got to look at the number on that. Usually in the case of kind of crossing over metric to English, there will be one number that is an actual number and the other number will be like a 1. So you don't look at the 1, but you look at the other number. So maybe we have that coming up shortly. We could look at it a little bit more. So for each of these, will these be considered measured or exact? If I have 3 coins, that is a exact number. Diameter of a circle is 7.902 centimeters. Measured, how many sig figs? 4, right? Uncertain right there. 60 minutes is 1 hour. Exact, yeah. So there you go. All right, so for the first one, how many significant figures we got? 2, sounds good. Second one, we do have 4, again, significant because of the decimal point in this case. Next one, 1, significant. These are not significant because we don't start counting until we get to the 8, right? And lastly, we have 3, all significant here because of the decimal point at the end, yeah? Very good, really good. They agree, even better. All right, so for each of these, take a moment and pick the one or answers that go with the question, I guess. So take a moment or so, see what you come. All right, let's take a look at the first one here. Which one has 3 significant figures? 2 looks good to me, yes. So 2 does. Again, these are not significant. Start counting here. All 3 of those are significant. First one has how many? 4 significant figures. The last one has number 3. 4 as well, yeah. So this is the correct answer. Which ones have all the zeros are significant? 2. So this is significant because of the decimal. These are not significant because we don't start counting until there. How about over here? Those are All significant as well. So it is 2 and 3 in this case, yeah? Because it is written in scientific notation, which means all those zeros right there are going to be significant because it's before the times 10 part. Question on that one? Remember again, written in scientific notation, that is where we assign our significant figures based on how it's written, yeah? Number of significant figures in 5.8 times 10 to the 2 is? Sounds good. All those numbers before the times 10 part. Looks like a winner. Any questions on that there? All right. Now that we understand what are significant figures, let's talk about what we do with them when we do calculations. So when we do calculations, we always want to give our answers to the proper number of significant figures. When you do a calculation, you always want to look at anything that is a measured number and not an exact number. And as I mentioned several times, your calculation that you do is only as good as your worst measurement. And that is what helps us decide how many significant figures, for example, we should have in a calculation. Also, why again it's really important if you are taking measurements that you take them to the proper number of significant figures, because if you screw up your measurement and make it worse than it should be, you also just screwed up your calculation, and it's going to be a worse calculation than it should be in terms of significant figures. All right, well, there's really kind of two categories of math that we do. We will multiply and divide. Now, if you multiply or divide, your answer should have the same number of significant figures as the number with the least number of significant figures in your calculation. So if you're multiplying, if you're dividing, or you're doing both really, your answer should end up having the exact same number of significant figures as whichever number in your calculation has the least. So again, it goes back to like your worst measurement is going to determine your calculation. So if I take 4.20 and times it by 1.3, I am multiplying, right? And this number has how many significant figures? 3. This number has how many? 2. That means my answer should end up with 2 significant figures. So if I pop this onto my calculator here, which one of the important things to remember about your calculator is it will probably maybe not give you your answer to the proper number of significant figures. And in this particular case on my screen, I got something like 5.46. That is 3 significant figures on my screen and not the right number of significant figures I need for my answer. I need to go here, right? Now we need to do some rounding, right? And normal rounding rules apply. 5 and above, we round up. Less than that, we just either get rid of the numbers or leave it alone and just, get rid of those extra numbers. So in this case, we're going to round up, and we should end up at 5.5, which has 2 significant figures. Any questions on that there? Same rule applies if you were dividing numbers. You look at significant figures. So if you multiply or divide, you should always look at the number of significant figures. It is always the least number of significant figures is what your answer should be. The other sort of combination of stuff that we do is a little adding and subtracting. So if we add or subtract, your answer should have the same number of decimal places as the number with the least number of decimal places. So when we add or subtract, we are not looking at significant figures. We are looking at decimal places. It is still the least number of decimal places. So if I take 1.25, add it to 3.3, add that together. I'll try without the calculator. 554. I should look at this because I'm adding, and again, not look at significant figures, but look at decimal places. This first number has how many decimal places? 2, right? Second number has 1. That means my answer should end up with 1 decimal place. So once again, I look to the number to the right. It is 5, so I'm going to round up in this case, and that would give me the proper answer of 4.6. 4.6 has 1 decimal place. How many significant figures does it have? It has 2 significant figures. That might be important if you took that 4.6 and now multiplied it by a number, right? Now you got to switch to significant figures. So it's important if you are especially doing a multi-step calculation, you got to kind of keep track of what you're doing so you know where to finish at in terms of your answer. Now, you may have something like this maybe. 2.55 plus 4. And I add that together. That is a 5 point and a 6 in the front. First number has how many decimal places? Next number has no decimal places. That's like a whole number, right? Smallest number of decimal places in this case is none, a whole number. In this case, you would round this thing up to lucky number 7 in this case, because we would have to round this way. That is because if those were really measurements, 2.55 was a measurement and 4 was a measurement, which one is a better measurement? The 2.55, because your error is where? Your error is here, right? Your estimation. Here with the 4, your error is way over here in the ones place, right? So again, you're saying, I think it's 4, could be 3, could be 5. That's a lot of error. And because you have a measurement like that, the best you could do on that calculation is that what limits how good your calculation is that kind of measurement that you have or that number that you have. Question on that there. Well, after we do everything together, I don't know. Let's say I did 422 times 3.678 divided by 1.2. Why don't you try it and give the answers to the right number of significant figures? I will too, since I just made it up. We'll see how we did here on this. All right. So if we were going to do this math, normal sort of math function rules would tell us what part of the calculation should we do first. Yeah, whatever's in the parentheses is what we should do first. We are multiplying there, right? So since I'm multiplying, I'm going to be looking at significant figures, right? So I'll get the answer in just a second, but this first number has how many significant figures? 3. This number has... That means, technically speaking, when I get my answer for the top part, how many significant figures should I end up with? I should end up with 3 significant figures up there on top, right? Now I'm going to finish the calculation, right, with a little division, right? I'm going to take the top number and divide it by the bottom number. So since I'm dividing, I should still be looking at sig figs. I already know my top number should be 3. This bottom number is how many? 2. So when I'm all said and done, how many significant figures should my answer have? Should actually have 2 significant figures based on that, right? So you got to kind of follow the step through. So if you multiply the top there, 422 times 3.7, no, punch it in right, 3.67, still not right, hit it, 7, 8. Maybe if I just punch really hard, it'll work better. 155.2.116. So that's what you get up there on top, right? So my first piece of advice would be Should I round that right at this point to three significant figures? The answer is you probably want to avoid rounding until the very, very end. So if you round a number and you're going to take that number and kind of use it in the next calculation, get a number, take it and use it in another calculation. And if you round a lot all the way through, you may end up with an answer that's really far off from the true answer because you did a little bit of rounding. So every time you round, you actually change the number. But it is important to kind of keep track of where I should end up. So sometimes people will put like a little line above the number of like that's where I should end up really, but I'm going to keep the whole number, and that's really good practice to kind of keep the whole number till the very end. Now I'm going to take that obviously and divide it by 1.2, and on my calculator I got like a 1293.43 staring at me. And at this point, I could go through what we did over here if I didn't already and figure out where I should end up. And I should end up at two significant figures, which takes me to which number in my answer? Takes me to the 2, yes? I do need to look at the next number, which is a 9. That means I should round up. Is the correct answer 13? Right, it is not, even though it has two significant figures. That goes back to the earlier example of here I owe you about $1,300, here's $13. That's a very big difference, right? So again, we don't want to do extreme rounding. I could go 1300. That is how many significant figures? And it means the same thing. Can I go 1300 with a decimal? No, because now I have how many significant figures? 4, not good. I could also go 1.3 times 10 to the 3. That has how many? And that's okay too. You could go scientific notation if you wanted to as well, right? Any questions on that there? So it's important, especially if you're doing multiple steps in a calculation, to kind of keep track of everything. Because what determines where you end up in terms of your significant figures in your answer actually could be like the first part of the calculation you did way back when, right? So you want to kind of keep track of it as you're going through it so you can figure it out. Any questions on that there? Yeah. Say it again. It cannot, although 1 point like this, is that what we're asking? 1.3? Yeah. Although 1.3 does have two significant figures, again, remember that you do not want to change the meaning of the number. So 1.3, and if you just think about money is a good way to remember it. If you were to be paid $1,300, $1,300, and somebody gave you $1.30, that is definitely not the same meaning in terms of that number. So although you did round it to the correct number of significant figures, you change the meaning of that number, and you never want to do that when you round. And it is, I'll be honest with you, it is a very, very common error that people make because they are very concerned, which they should be, about giving the answers to the right number of significant figures, that they kind of forget that other part of, oh, did I just really like make that number something different? So you never want to do extreme rounding. You want to make sure you round it to the proper number of significant figures that once you're done rounding, it basically means the same number. And if you had $1,293 and you got $1,300, it's basically the same value and it represents the same amount. And you never want to change the meaning of it. But it's very, very common people do that because they're trying to get the right sig fig. So they just do that. Other questions? Yeah. Absolutely, yeah. So you could do either one. They are both of these are acceptable answers, whichever way you want to do it. Other questions? Okay. So again, our normal rounding rules. Don't do any extreme rounding or anything like that. Well, what happens if we had something like, let's do something like this. Let's do 1.2 times 10 to the 2 divided by 42.5 plus 3.6689. So give that a go, see what you come up with. I'll do it as well. See if we come up with the same thing. Look, so once again, if I were to sort of follow math rules here, which part should I do first? I should do this guy first, basically, right? So here we're dividing. So because we're dividing, we're going to be looking at significant figures, right? So top number has how many significant figures? Has two significant figures. Bottom number has three. So really, when we get our answer for this part, it should end up at two significant figures. This is a little scientific notation reminder, right? So like a 1.2 exponent button, right? And a 2. Divide button, 42.5, and then equals. And if you do all that, make sure again you do use your exponent button. You're going to actually end up with a number on your calculator of 2.82352941 plus 3.6689, right? So you got something like that. Now, technically speaking, based on the first part of the calculation we did, we should end up at two significant figures, which takes us to which number? It takes us to the 8, right? So technically speaking, right about here at this 8 is where that number should end up, right? Again, I'm probably not going to round at this point. I'm just going to take the whole number in my calculator, and I'm going to add it to my next number, which is 3.6689. Hit an extra digit there, probably not good. And when I do that, now on my calculator, I got 6.4924, 29412 on my display there. Now, the last calculation I did was a multiplying, dividing, adding, subtracting. The last thing I did was, in terms of math, I did adding, right? I added the last two numbers. When I now switch to adding, am I still looking at significant figures? No, I'm now looking at decimal places. And this is where the very first calculation we did comes really into play, right? Because if we rounded correctly, or did round our very first number, it should have two significant figures, right? Which would take us right about there, yes? And technically speaking, what's in the box, we're now going to look at decimal places, right? Because now we're adding to the next number. That means that this guy has technically how many decimal places? One decimal place, right? Even though there's a bunch of numbers, but because this should be two significant figures, that is the only decimal place right there that's important. When we go to our next number, it has how many decimal places? It has 4 decimal places, right? That means my answer should have how many decimal places? 1, which would take me to here. And now I look at the 9, and I should round to 6.5. So really our ending answer is actually determined by this calculation that we did, right? It's actually not necessarily the last one, although we are looking at the last calculation in terms of should I look at decimal places or should I look at significant figures? But really the ultimate thing that determines where we end up in this particular example is actually the first one, right? Any questions on that? So you may do definitely some calculations where you're doing multiple calculations, one right after another. I would again try to avoid rounding till the very end, but you do kind of got to keep track of, where things actually should be. So if you need to, you can put a little line above it where you should be, or do what I do, just kind of write like 2 significant figures, 3 significant figures. I should end up with 2, something to remind you. And then you got to kind of put all the calculations you did kind of together and kind of go from the beginning to the end and figure out where you should end up. In this case, we first were looking at sig figs, and then at the end we had to look at decimal places, and sometimes that does happen. Any questions on that there? No? Okay. All right. So again, just some normal reminders on rounding. 8.4234. If we want 3 significant figures, that is going to take us to the 2 here. Next number is a 3, so we just drop it. And if we wanted 2 significant figures, that's going to take us to the 4. and the next number would be a 2, and we would drop the rest of it again because it's less than 5. If we wanted 3 sig figs on the next one, that's going to put us here. We want to go round up because the next number is an 8, gets us 14.8. And if we want 2 significant figures, that's going to move us over here. We would look at the next number, which is a 7, and round up, and that would be a 15. Here, we want 3 significant figures, which would take us here. We do want to round up in this case to 326. Once again, in this particular case, I do have 3 significant figures, but is 3256 and 326 the same number value? It is not. So here we do need to add a 0 to maintain the meaning of it. It's okay to do that in terms of significant figures because I did not put a decimal point anywhere there, right? So that 0 at the end is not significant. It maintains the 3 significant figures, but it maintains the actual meaning of the number more importantly, right? And I definitely would not want to put a decimal point at the end because then I would end up with 4 significant figures, right? So these are things you want to kind of think about. Again, sometimes people get in the habit of like, maybe I should add some zeros or put some decimals in. Again, it might look more chemistry-like or something like that. So you don't want to do that. It looks more science-y if you put some extra things in there. We're going to 2 significant figures. Same deal. 2 significant figures would take us to here. We would round. Once again, we cannot leave it at 33, even though it is 2 significant figures. It is a very different meaning. Here we actually need a couple of zeros in this particular case to maintain the meaning of the number. And once again, we would not want to put a decimal. Could we also write in scientific notation? We could. And we would do 1, 2, and 3, 3.3 times 10 to the 3. Here we would not want to add those extra zeros if we wrote in scientific notation, because if I wrote it like this, I now have 4 significant figures, right? Too many for what we were looking for there. So again, you want to be careful of putting zeros, taking zeros away. You want to kind of end up on the right path there. All right, so round this to 2 and 3 significant figures. All right, so let's take a look here. 3 significant figures, starting with this number, would put us to the 4. We do look at the next number to the right, and that's 5 or above, so we do round up. So a 3.15 would look good. 2 significant figures would put us at the 1. We would look to the number to the right there, and that's actually a 4, which means we would actually drop in this case 3.1. Again, we would not keep those as zeros because now how many significant figures does it have? That's 4. That now is significant, and that's not what we're looking for in this case. Any questions on calculations, rounding? Seems like a good place to stop, I think. All right.